Welcome back. This is Allen High School, and we are doing chemistry for AP and IB. And we're finally going to be working into our structural models. And there are two main structural models that we're going to be dealing with that are built on one another. The first is called an orbital diagram. Now, an orbital diagram gives us the most information, but it also is a lot of work and a lot of space to be filling it up. And so it gives us maybe too much information. We're going to go over it, and then we're going to see how to simplify it into an electron configuration. Now, electron configurations are a little simpler, especially there's a shorthand way we can do it, but they're lacking a key point of information that an orbital diagram gives us. So we need to pick the right model for the information that we're seeking. So let's start with our orbital diagram. Orbital diagrams help us understand and explain bonding issues. That will be our next unit. We'll go from the atom to bonding. They help explain a particular property of elements, and that is whether or not they are attracted to a magnetic field. So some are and some aren't. And it's typically a weak attraction, but still, why is that? And we see that from the orbital diagram. So those that are not are said to be diamagnetic. So that's a vocab level word. You're not going to have to do a whole lot more than do an identification or use an orbital diagram to explain why a substance is diamagnetic, or conversely, why it is paramagnetic. And we need an orbital diagram to do this, or at least we need the outer part of an orbital diagram to determine whether a substance is diamagnetic. And again, diamagnetic is not attracted because all of its electrons are paired. If we have unpaired electrons, then it would be paramagnetic. So let's go on and take a look. First, we need to talk about the rules. These are the guidelines that have been observed. It's not like we're telling the electrons what to do. This is what scientists have observed in terms of electron behavior. And the first rule is called the Aufbau principle. Aufbau is German for building up. And what that says is that we're going to be placing our electrons into the lowest energy orbital available. Well, hopefully that's logical, because remember we said we want to maximize the attraction of the electron for the protons in the nucleus. So man, if there's a spot open, they want to get near. And it's like at a concert. If there's a spot open, people want to get near the front to be as close as they can to their favorite rock star. Now, the second one is called Hund's rule, named after, you got it, a dead guy, Hund's rule. Now, what Hund's rule says is within a sublevel, now not an energy level, we're talking about within a sublevel. This will be particularly important as we fill the P, D, and possibly the F sublevels. So within a sublevel, because we're looking at orbitals that are degenerate, meaning again, same energy, orbitals are going to go, or electrons are going to go into orbitals unpaired before pairing. Well, hopefully that's logical too, because we said that we want to minimize electron repulsion. And to pair up is going to have a little bit more repulsion than if they are in separate orbitals unpaired. Now, if we went back to that little analogy that we had about being in, a train and having only bunks, the first guy that comes, he's going to take that first bed. Second guy that comes in, he's going to go into the empty bed if there's an empty bed. And the third guy then gets forced to pair up. So they're not going to pair up unless they have to. All right, and that's again to minimize electron repulsion. These are key as part of our justifications. It's not just enough to know the why anymore. The why. let me go back. It's not enough to know the what anymore. That's pre-AP level. We are AP IB level, and so we need to be able to explain the why. And then finally, we've seen this before. You observed this in one of your examples, but it has a name. The Pauli exclusion principle. Pauli is another wonderful scientist who is now dead. Pauli exclusion principle that states that no two electrons can have the same 4 quantum numbers. Now, this is going to be accomplished by putting electrons with a +1/2 spin and a -1/2 spin when they have to share an orbital. So they may have the first 3 the same, but then that 4th spin quantum number will not be identical. So those are the guidelines. Now, let's take a look at an orbital diagram. And for now, I've lost my lines on this. For now, I want you to trust me. It gets a little mixed up. So we have our 1s orbital. We depict that with one line. Our 2s orbital with one line. Our 2p has 3 lines. 1, 2, 3. Our 3s has 1. Now, so far, we're going in an order that would seem very logical because I did tell you that as you increase n, you increase energy. But then look what happens. The 4s ends up to have a little bit less energy than the d. And so we're actually, according to Aufbau principle, going to be filling in that 4s before we do the 3d. Now, we're going to be able to determine this from our periodic table. So trust me for now that this is the order, and we will be looking and see that the periodic table gives us everything we need to know. And then again, here we go, filling the 4s before we do the 4d. Now, there are people and there are books who use this little tree diagram to help with this order. And I don't like that tree diagram. I'm not going to use that tree diagram because the periodic table is much better. We can learn so much more if we understand electron configurations using the main tool that we always have at hand, which is the periodic table. So again, I'm going to show you how we fill, and this order will be ultimately revealed. Now let's do I want to make one more point. Now, this is not to scale. I wish I could draw it to scale, but I can't do that. It just doesn't matter for me. Energy is going up. You are going to be able to draw these, energy going left to right if you want. But I want you to notice something in here as well. In addition to this kind of mix-up of energy here and here, do you notice that the P sub-level is higher in energy than the S sub-level? And that's where I was mentioning earlier that L does give us a little indicator of energy. Yes, N is our primary or principal energy indicator, but L just gives us a little help there. Now, I want to show you how we would do selenium following our rules. Selenium has 34 electrons, and when we follow those rules, we are going to get the ground state. Not an excited state, but the ground state of a substance. So here's what we're going to do. Aufbau says go lowest energy. Hund's rule doesn't apply for the S. Pauli says spins opposite so that no 2 electrons can have the same 4 quantum numbers. Aufbau says go to the next lowest energy. Pauli exclusion says spins opposite so that no 2 electrons will have the 4 same quantum numbers. Aufbau says go to the next lowest. Now we have to invoke Hund's rule. Before we pair up, we're going to put them in unpaired first, and that's key. Now it's only within this sub-level. I'm not going to go any higher because these are equal energy. So the attraction to the nucleus is the same. Therefore, we can minimize repulsion by putting them in unpaired before we pair. And again, Pauli spins opposite so that no 2 electrons can have the same 4 quantum numbers. Aufbau says go to the next lowest energy. Oops, missed a couple orbitals there. Pauli Hun says spins go in unpaired into a sublevel before they pair, and when they pair, Polly says pair opposite. Now, I am not quite at selenium yet. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, and I have to put 34 in here. So I'm going to keep going. Aufbau, Polly. Now we have Hund. Hund's rule, I'm in a sublevel. I'm going to put them in unpaired before I pair them. And now I've got selenium. I have 4 more electrons left. Aufbau says go to the next lowest energy. Hund says unpaired before paired. Polly says spins opposite. So no 2 electrons can have the same 4 quantum numbers. Now I want you to look at a couple of things before we move on to another example of this. The first is that, if you'll notice, we have 2 unpaired electrons. Notice that everything prior to that is paired. That's why if you want to determine the number of unpaired electrons, you have to at least do an orbital diagram of your last sublevel you were working with. Now, since we have unpaired electrons, we call this paramagnetic. So that's our orbital diagram. Let's go ahead and write this in a little bit more of a shorthand manner that we call an electron configuration. We'll get the periodic table to help us with that so that we don't have to do orbital diagrams every time. I have 2 electrons in the first energy level, S sublevel, and I have 2 electrons, so I put an uppercase there. No comma, follow right away with my 2s2. I have 2 electrons, I superscript it. Then I go to 2p. If you look up here, I have 6 electrons. You notice this doesn't give us any indicator of paired versus unpaired, but it's a lot easier to write. And then I'd have 3p6. That's for that. Then I'm going to 4s, the same order I filled before. We're going according to energy, left to right. 4s2. And then I'm going to have 3d10 and 4p4. So that's my ground state for selenium. And if you want to know whether there's unpaired electrons, you really have to look at that last sublevel there. So this is going to get too long, I think, if I keep pushing forward. So let's come back and do a few more of these, and I will show you how our periodic table gives us this odd order. Remember, distance stays true. All right, what that means is that the 3D is closer to the nucleus than the 4s. But because the electron has to move in a more complicated region with a greater angular momentum, this is a little bit higher energy. So it's a little simplified, but it'll work for now. So for now, signing off.